Snake is a classic pixel-based game where the goal is to eat as many apples as possible while avoiding the snake body and walls. The challenging thing about this game is that the snake's length increases with every apple eaten. Since this game is so difficult to master, why would I spend my time mastering it when I can spend my time building something to master it for me? That's why I'm going to create an AI to play Snake. Searching for AI Snake does return some results, but there's a common problem between them all. They all suck. Don't get me wrong, it is impressive that a computer could be taught how to even eat a few apples, but all of these snakes are making very obvious errors and not filling the board. Although I want to create an AI snake, research in automated snake games, better results can be found. There are many implementations where the snake uses different searching algorithms to find a path to the apple. Some work perfectly, but these snakes can still become trapped based on poor past moves. Some automated games also incorporate what's called a Hamiltonian circuit. A Hamiltonian circuit is, in this case, a path that goes through every single space on the board and ends in the same space it started. It's the snake playing on the right side right now. If the snake were to follow this Hamiltonian circuit, it is guaranteed to fill the board from eating apples. Depending on the board size, there can be many Hamiltonian circuits, or none at all. The problem with the snake only following a Hamiltonian circuit is that it's incredibly slow and boring to watch, since the snake repeats the same path over and over again. With this information, I set the following goals. I want to create a true AI snake with reinforcement learning that doesn't use any searching algorithms. I want to have the snake to be able to fill the entire board, and I want to have the AI make intelligent decisions based on the current board state. There are many different reinforcement learning algorithms, such as DQN, DDQN, A2C, TRPO, PPO, and many others. For this project, I will be using PPO, which stands for Proximal Policy Optimization. I'm using PPO in this case because it is stable in its learning, meaning as it learns new things, it doesn't forget the past things it has learned. It is also sample efficient, which means it can learn from less information and faster compared to other reinforcement learning algorithms. And the last main reason for picking PPO is that it performs well in stochastic environments. A stochastic environment is an environment that is random and unpredictable in nature. Because each new apple spawns in a random area, Snake is inherently stochastic. To explain how PPO works under the hood would take a whole video on its own, so I'm not going to go in depth on the math behind it in this video, but if you're curious, here are some formulas. I'll also include a link to some documentation that explains these in the description. In general, PPO works by outputting a move based on a given observation space. An observation space is an array or list of numbers, where each number represents something. In this case, the observation space is going to be the game board. People have tried many different observation spaces for Snake to limit the complexity of the game, such as giving only a small image of the board centered at the head of the snake, giving the past moves of the snake, or giving the directions that the snake needs to move to get the apple. The problem with this is that all of these observation spaces give up necessary information for a simpler observation space, which benefits the learning in the short term, but hurts the performance of the snake in the long term. That's why I'm going to be using this entire board as an observation space, as this is the same information a human uses when playing the game. In order to give the board as an observation space, we first need to know what an image is. Images are really multiple pixels, where each pixel is composed of 3 values that represent red, green, and blue. The image that the AI receives can be simplified by making the image a single brightness value per pixel instead of 3 values per pixel. This is also known as converting the image to black and white. Doing this simple step reduces the information the AI needs to learn by 2/3, which is a huge reduction in complexity. The next step in reducing the complexity of the observation space is to use as few different values as possible. Instead of representing the image with a wide range of numbers, we can reduce the different numbers the AI needs to learn. This can be done by representing the snake, apple, and empty board as 3 different values. So, using this idea, the observation space can become something like this, where the empty board is 0, the apple is 1, and the snake is 2. Using these reductions of the image simplifies the information the AI needs to learn while also maintaining all the information it needs to be able to play and learn the game. But even with these steps, the snake will fail to learn how to play at a high level. Why? Well, let me show you. In this image, what do you think the best move the snake can make is? This should be easy, it's to the right as it will eat the apple. Except it's not that easy, because if the snake were to move right, it would be dead, since this was the past few moves. As you can see, the difference between a human playing snake and PPO learning to play snake is that humans have a memory of the past moves that were made, which means you don't normally have a problem confusing which way the snake is moving, but if you were randomly given an image, like this one, you wouldn't know which way the snake is moving. This is the same problem that the AI will run into, as this algorithm doesn't have a memory of the past moves. Thankfully, there are a few ways to get around this. The first way, which you may have already thought of, is to give the snake the past few board images and the current board image. This idea is valid and often used. It's such a common method that it has its own name, frame stacking. The problem with this solution is that it greatly increases the complexity of the observation space, which we want to keep low. If you include just one past image, it doubles the amount of information given to the AI. This creates a new challenge of how do you balance the number of past frames and the complexity of the observation space. You don't want to give the entire history the snake has played, as that would create a huge observation space. But if you give it too few frames, it can still be missing vital information. For example, consider the same previous snake. In this case, having just a single past frame is enough information to see where the snake is moving. But now consider this example. This is the previous frame on the left, and this is the current frame on the right. Seeing the previous frame still doesn't give enough information. In fact, this snake shows a problem with frame stacking in this game. No matter how many frames you were to stack, the snake could have been looping for just one more frame. Then the AI wouldn't know where the snake was heading. These problems bring up another solution to giving the snake a memory. What if instead of giving you the past few frames, I instead color the head a different color? Now, with this original snake, it's still possible to see which way the snake should move, and in this example, it also gives enough information to determine which move the snake should make. This keeps the observation space small, while also giving the AI enough information to determine how to solve this problem. This method still has a problem though. What if the snake were to be positioned like this? In this case, it's still impossible to tell if the snake should move left or right. This problem can be fixed by using the same concept on the tail as with the head. If you were to color the tail a different color, it's possible to determine which way the snake should move. But yet again, this isn't foolproof. For example, consider these two boards. One of them, the snake is guaranteed to lose, and the other, the snake can easily escape. We want to eliminate this confusion, as the AI may learn to avoid this situation even if it can be optimal in some cases. The solution to this problem is to color each part of the snake a different color. Once we color each part of the snake, you can quickly tell the difference between these two boards. If we keep this coloring consistent, it gives the AI all the information of the past moves, while also keeping the observation space small. Going back to the observation space, this coloring can be represented as numbers. So if we keep the empty board zeros and the apple 1, we can now change the numbers that represent the snake from always being 2s to being a 2 if it's the head, and 37 if it's the tail, with the body parts between the head and tail being numbered in order up to the tail, which would look something like this. If this is the colored snake, this is the observation space that would represent it. See how the tail is 37 and the numbers decrease by 1 each time as the body gets closer to the head, and then the head is 2. This jump between 2 and 19 is done to keep a standard representation of the two most important things, the head and the tail. This is important because it allows the AI to look at the area surrounding the head without getting confused on which value represents the head. It is also important that the tail stays a single value because it allows the AI to learn which part of the snake is going to be disappearing next as the snake moves. Now that we have an observation space to give the AI that contains all the information it would need to successfully play, a reward structure needs to be set up. As I stated earlier, PPO is a reinforcement learning model, which means it is going to learn how to play on its own without me specifically telling it how to play. For a reinforcement learning model to learn how to play Snake, it needs a way to know what it should even be doing. To guide the reinforcement model in what its goals are and how well it's completing these goals, a reward structure needs to be set up. The more rewards the model gets, the better it's doing. The model learns that it should do more of whatever gave it a high reward and avoid doing things that lower its reward. In Snake, the reward structure is simple on the surface, but in reality, difficult to tune. The reason for this is that machine learning follows a very strict structure and will often find ways to outsmart you to maximize its rewards. Let's start with the main goal of this game. Eat as many apples as possible without dying. A reward structure that follows this goal can be made by giving the snake a reward when it eats an apple and taking a reward away when it dies. Training a model with this reward structure can result in a few different outcomes. If the penalty for death is large, the snake will avoid dying at all costs, as it won't learn apples give a positive reward before it discovers that it can go in a loop forever without dying, allowing it to avoid the death penalty, but not growing the snake any larger. If the penalty for dying is small or 0, then the snake goes directly for the apple without considering if the move will lead to its death or not. This is fine while the snake is small, but as soon as the snake gets long enough, it is going to trap itself. Modifying this reward structure for better performance, we want the snake to avoid running into itself, so a larger death penalty is kept. But instead of giving the AI a reward only when the snake eats an apple, it is also rewarded for making moves towards the apple, as we want to avoid the snake getting stuck in an infinite loop while avoiding the death penalty. Training a snake with this reward structure, again, results in the snake being in an infinite loop. However, this time, it's not stuck in a loop because it's trying to avoid the death penalty, it's stuck in a loop because it's maximizing its reward. Since it's rewarded for moving towards the apple, the AI learns that if the snake loops infinitely, it will be infinitely rewarded. Remember how I said it likes to outsmart the reward structure? This reward structure can be modified in a few ways to try and fix this. The first way is to punish the AI if the snake moves away from the apple. The problem with this is if the punishment for moving away is smaller than the reward for moving towards the apple, the snake will continue to loop as before. If the punishment is equal to the reward, then the snake has the same problem as before, where it will try to avoid the death penalty and start looping. It would have a net reward of 0, but since it won't ever die, it is as if the snake isn't being rewarded or punished for moving toward or away from the apple. And if the punishment is larger than the reward, the snake will actually go straight for the apple without caring if it runs into itself, because it will learn if it tries moving away from the apple to avoid death and then dies, it has a lower reward than if it had just died without moving away. Because of these reasons, giving a punishment when the snake moves away from the apple is not ideal. Another solution to fix the looping problem is to end the game after so many moves are made without eating an apple. For example, in this case, the snake can move to every position in the board and still eat the apple within 36 moves. To give the AI some leeway when exploring, we are going to set a maximum move count of 40 between eating apples. If the AI reaches 41 moves without eating an apple, it is penalized as if it died and the game is ended. Training an AI with this reward structure of penalty on death, max moves, and a reward when moving closer to and eating an apple creates an AI that does really well in Snake. It avoids deaths and eats apples consistently. But there's still a problem. Remember, the AI wants to maximize the reward. So, in order to maximize reward, the AI learns that if instead of eating an apple as fast as possible, it can instead loop until it's about to run out of remaining moves and then eat the apple. Doing this results in the snake eating an apple, doing a bunch of useless moves, and then eating the next apple, which is not ideal and can even be slower than following a Hamiltonian circuit because it purposely avoids the next apple, even if it would be easier to eat it. To fix this problem, the reward given from eating an apple can be decreased by slightly more than the reward the snake receives for moving closer to the apple. For example, let's say that the reward for eating an apple is 100 points, and each step closer to the apple is worth 1 point, and for every point gained for stepping closer, 1.5 points are deducted from the apple reward. So, if the snake makes 10 moves closer to the apple, and then the reward given for eating an apple is decreased by 10 times 1.5 points, which is 15 points, subtracting this from the apple rewards gives 85 points as a reward for eating the apple instead of 100 points. Training an AI using this reward structure yields by far the best results, which means it's time for a training montage. As you can see in the early stages, it loops consistently. It has learned how to avoid death, but hasn't learned the penalty for dying after the max amount of moves have been made. You can also see that it learns how, once it gets close to a maximum number of moves, it knows it's going to get punished for moving back and forth, so it decides to go eat the apple. This wait after moving back and forth before it eats an apple eventually disappears because of the reward structure we set up, where it gets more reward for eating the apple faster. You can see once it starts to eat a few apples, it improves very quickly. You can see that it's able to fill the board in its entirety now. It's still not perfect, as it's making a few useless moves and sometimes doesn't manage to fill the board, so I continued training a little bit longer to try getting the best moves that it can possibly find. The reason for this coloring weirdness is because I'm taking the observation space that the snake is seeing and converting it into an image so you can understand it and comprehend the colors and different patterns better. As you've seen earlier, all the other AI snakes that you can currently find online pale in comparison to what this AI is able to do. Now, I wanted to push this project some more, so I decided to make this a little prettier because the images that you were seeing weren't perfect and were kind of ugly with the colors. And with some modification and testing, I was able to get this working on multiple board sizes on different dimensions using just one AI. Training this model for a few days, yes, it did take this long, I was able to get even more impressive results. As you can see, it can easily accomplish a 4x4 board, which it should easily be able to do, as you had seen it complete a 6x6 earlier. Now remember, some boards have Hamiltonian circuits and others don't. If a board has odd dimensions on both sides, the x and y, won't have any Hamiltonian circuits. So the snake won't be able to play in its same way that it can with Hamiltonian circuits. It has to wait until there's one apple left and then basically trap itself in eating that apple. Now, this AI still isn't perfect on all board sizes. On a 6x6, we'll say it is. As you can see, it is trapped itself, and then it gets that apple, so it does technically complete the game even on a 5x5 board without Hamiltonian circuits. I'm going to start moving up a little faster. You've already seen a 6x6. I'm going to show you an 8x8. As you can see, it's much, much larger than a 6x6. Remember how as you increase dimensions in X or Y, it doesn't just increase linearly, it's scaled much faster than that. As you can see on this 8x8 board, it's making very intelligent moves, filling in board spots that it doesn't want the apple to spawn in later, and taking chances on apple spawns that are very unlikely. So it will leave some gaps if it knows that it's unlikely. As you can see, it can easily complete an 8x8 board. Now, all of these aren't perfect, and it can still fail. This snake is based on what it has seen and learned and trained on. Because apples spawn randomly, there's many possible combinations of this game board, so it's not perfect. Moving up onto a 10x10 board, you can see how much more complexity there is compared to a 6x6 board. It can move much more freely at this early term and can make much more complex moves, which you will see in this board. The snake often likes to follow a clockwise path. I'm not sure why this is, but it learned how to do it. I didn't teach it any way, shape, or form. It learned that this was the best based on what reward structure it was trained on. There's a sort of joy in creating an AI that plays Snake compared to some sort of searching algorithm or Hamiltonian circuit, since I don't even know if this is going to fill the board or if it's going to fail on this run. As you can see, it's able to successfully complete a 10x10 board. Moving on to a 12x12, it is reaching the upper limits of what this AI can do. As you can see, the snake does still sometimes trap itself. This can be fixed by training the AI for even longer, but I've already trained this for many days, and it's the best that I can find online, so I'm going to call it good and not spend any more time training this, because it does still sometimes, if not most of the time, complete the board on a 12x12. Because a 12x12 board is so large compared to a 6x6, remember, it's double in X and Y dimension, but it's 4 times as large in the total number of spaces compared to a 6x6. Because of this, it greatly increases the number of different combinations that the snake can be in, and the learning time for these boards greatly increases. And as you can see, it's able to complete a 12x12 board. Moving on to a 14x14 and speeding up a little bit more, just because the boards are so much larger, it starts to take a lot longer to complete. (14x14) is about the upper limit for a square board size of this model. This model actually is trained on everything between a 4x4 and a 20x20 and everything in between. So it does a 4x20, a 5x20, and a 20x4. All of those this single model is able to do. However, it isn't perfect at the larger ends because of how the model is trained. It takes a very long time for it to learn a 20x20 board, say, for example. As you can see, it still can complete a 14x14. Moving on to a 16x16, it most likely won't complete this board, but I will still show you what it can do. As you can see, it wasn't able to completely fill the board, but it got very close and is much better than anything I'm able to find online. I'm going to move straight up to a 20x20 and skip 18x18 just because it's not going to be able to complete an 18x18. It's not going to be able to complete a 20x20, but this is the largest that this AI can do. So I'm going to show you guys. As you can see, it wasn't able to complete the board, but it still did very well for how many spaces and moves and possible combinations of the snake there are on a 20x20 board. If you search for snake, you can actually go in browser and play this game on your own and see how you compare to the AI that was made in this video. If you liked this video, make sure to like and comment. And if you have any ideas on what I can teach an AI to do next or to improve this AI, make sure to comment that below. Thanks for watching. I'll catch you next time.